Okay, so a commonly seen question that I've seen in the group chat is most people are like posting like pictures of their data tables like I have here on the screen. And we see most often that get rid of this thing. That right around here, people usually have these values. For the alquat one will normally be normal. Then this will end up being like 19, and this will be 29. And that is due to people not subtracting the aliquots, right? Because what we need to do is, in order to get aliquot 2, we need to subtract mass of aliquot 1 from, or not the mass of aliquot 1, but the first mass from the second mass. So that'll just be 119, not 119, but 129. 459 minus 119.48. That'll end up giving us 9.961. And then you just basically do the same thing. So you have to subtract the preceding mass, so up here, from the aliquot you're trying to find. It depends. What were your values?
Like for the masses, or for the stopper, I had 102.591, and then 112.488, and then 122.452, and then 132.441.
Okay, so where did you have the 9.9?
When I got to the mass of the aliquot 2, I was wondering if it was like 9.9, or we have to go like 9.9, like
if it goes, did it just end up being like 9.9 exactly?
No.
Okay, so go to 4 decimal or 4 sig figs. So 3 decimal points.
Okay, thank you. And then for the standard deviation, can you do like an example of that? Because I know we can put it in Excel, but I just want to know how to do it like manually.
Manually?
Yeah. Or at least like you don't have to do it. Like, what values do we use?
I'm gonna do it. Let's start a new file. Okay, so the formula for standard deviation is, this is our symbol for standard deviation. It's the square root, the sum of our values minus the population mean squared all over the population. So if we were to take our volume, so mine are 9.907. This is for the pipette. Then 9.988. And 9.899. These are what we'll be putting in for x sub I. And then we'll also need to calculate the average. So we can just go ahead and add these up and divide by 3. And we will get 9.931. So that is going to be equal to our population mean. Then we can do this and start solving. We'll just do the entire thing by hand. Well, we'll write it out. We're not actually going to be multiplying these decimals by hand because I don't want to do that. So we'll do 9.907 minus our population mean of 9.931. Square this. The next one is 9.988 minus 9.931 squared. And the third one is 9.899 minus 9.931, also squared. So this is going to be x sub I this is all our population mean. So this is going to come out to be 0.988. Zero, 249. For third one, 0.01024. And then because of the sigma here implies we add all of these values up. We get 0.004849. Now we divide by our population, which is 3. Which then comes out to be 0.001616, which is very different from the Excel value that I have. And then we take the square root of this. So we get 0.040203. So that's how I calculate standard deviation by hand. And then for Excel, I can just go over here. And then all you need to do is just type in the formula for, like, if say you have all these values over here that you want. Equals stdev.p. Then you're gonna want open parentheses. You'll put your first cell in that has your value, or your first value, which in this case is B1. And then you want a colon, because if you do semicolon or comma, then it's only going to go cell by cell, whereas we want all of the cells. So put a colon, follow it through, and we close out the code, and we get our standard deviation.
Okay, thank you so much. That really helped.
Yep. So now we've basically covered like how to fill out your data table, since all you have to do is really just repeat this for your graduated cylinder and your burette measurements. Now we will go to, guess what is kind of part 3. So what is the difference between accurate and precision? Accuracy is how close you are to the actual values. So we know like the density of water to basically be 1, but that varies with temperature, as we've seen. And so accuracy would basically be like, if, let's just go back here. If your, say your measurement was 9.966 for your mass, well, let's see. Basically, in this sense, you're trying to get as close to 1 as possible. So with accuracy being how close a measurement is to 1, it's sort of like how close you hit the bullseye or something like that. Then precision is how close the set of measurements you have are compared to each other. So at this point, instead of aiming for the bullseye on the target, you're now trying to like split the arrows and stuff. Splitting the arrows, then you've got great precision. Next, what to the following is not considered to be a piece of volumetric glassware? Well, we all use volumetric glassware in the lab, except the one, or if we really just look at the lab, it doesn't ask for measurements from pouring stuff out of a beaker. Therefore, we can then assume that the beaker is not a piece of volumetric glassware. Then part 3.1, once a reagent leaves a bottle, it should never be returned. Why is this? Well, you don't want to contaminate the entire bottle because that's going to be an expensive mess that the chemistry department doesn't want to deal with. Then what is the second solution you made lighter, darker, or was the second solution you made lighter or darker in color than the first solution? This is what would be predicted and explain briefly. This is the same question as number 6, as many of us have seen. And basically, lighter distilled water used in the dilution is going, or the second solution is going to be lighter because you are adding distilled water, which is clear, to the food or the dyed solution, which was that red solvent we had. And that's going to dilute the solution and thus make it lighter. 3, which of the following is important for achieving maximum precision, measuring mass using the top left balance. Well, that's like basically E, so all of the above. Then in step 2 of the procedure, do you think you have added a full 100 milliliters of water to the flask? Yes. Because I measured it with a beaker that was at the 100 milliliter mark. So I mean, it's safe to say that that was 100 milliliters of water that went into the flask. 5, here's one of the math problems. So we'll switch off of standard deviation. This will be uploaded to a Dropbox. How much of the 1.0 moles or molarity solution was needed to make 100 milliliters of 0.04 molarity salt solution? So we have our formula. M1 V1 is equal to 2 V2. All right, we know our molarity. That's going to be equal to 1.0. We know that we're trying to get 0.04 and we need 100 milliliters of it. We don't know how much of that 1.0 molarity solution we need. So after we simplify everything, this will come out to be 4. And then 1 times V1 is just going to be V1. So we get volume is equal to 4 milliliters. Next, 6, after the solution or dilution in step 4 is a solution lighter and darker. Lighter, as we saw, or as we said in step 2, because of the distilled water in the solution, diluted food coloring present in primary solution, thus giving it a lighter coloring. And then we'll just zoom in a bit here. section this little spot off for question 7, which asks, if 10 milliliters of the original 1.0 molarity stock solution was added to a 500 milliliter volumetric flask and diluted to the mark, what would be the new concentration? So we can just use little M1, B1 is equal to M2, B2. So we know that this is 1.0. Know that this is going to be 10. And we know that our volume equal to 500 but we don't know the molarity. So what we're going to do is simplify everything. This will become 10. This will become 500 times our molarity. Then we divide 500 over and we get 1/50 equal to M2. So that will equal 0.02. But in this case, we have 4 sig figs, so 2, 0. Then could a 3.5 molarity solution be prepared with any solutions already made in this exercise? Why or why not? Explain briefly. No, you cannot dilute to a higher concentration. Making the 3.5 molarity solution would basically require you to make a 3.5 molarity solution from scratch and not off of a solution with a lower concentration. And that wraps up everything. And oh yeah, the observation part for the lab. Basically, the 0.04 molarity salt solution is going to be clearer than the 1.0 molarity solution because the higher the concentration of salt inside of a solution, as light passes through that, it's going to start bending around the little like dissolved crystals in the solution and kind of give it like this very, very slightly hazy appearance. It's hard to see with the eye, but if you just stare at it long enough, you'll begin to see it. And then like you could also say how the 0.04 molarity solution was pink as opposed to the red color of the 1.0 solution.